In this video, we're going to dip our toes into learning how to analyze a proton or hydrogen NMR spectrum. We're just going to take a brief overview of the spectrum itself, take a look at what we see, and just start to learn how many peaks we would expect to see for different organic molecules inside of a spectrum. So here's our first NMR spectrum. A few things I want you to notice. At the bottom, we have a scale. It usually goes in a hydrogen NMR spectrum from 0 on the right to maybe 10 or 11 on the left side. The right side of the spectrum is the upfield side, and the left side of the spectrum is called the downfield side. So the right side is the upfield side, and the left side is the downfield side. And I remember this because Adolph Rupp was the coach of the University of Kentucky basketball team many years ago, and the Kentucky Wildcats play in Rupp Arena. So the right side is up, Rupp. So if you remember that, you can remember the right side of the spectrum is the up side of the spectrum, the upfield side. Now, when we see a spectrum, you'll normally see peaks that show up here, and they have different shapes. That's not a very good drawing. So most of the hydrogens we will see in organic molecules will be somewhere between 0 and 11 and 12. We picked a chemical in organic chemistry called TMS, which every chemist uses to tell the computer that we work on where 0 is. And the chemical that shows us where 0 is, TMS, stands for tetramethylsilane, TMS. Tetra because there's 4 methyl groups, these methyl groups right here. And those 4 methyl groups are on a silane, a silicon. And the reason that's important is silicon is not very electronegative. It's below carbon. So a chemist might say it's electropositive. It tends to release electrons away from it towards these hydrogen atoms. And remember, we're looking at these hydrogen atoms. So you can imagine that, or you can understand that these methyls, the hydrogen clouds, the electron clouds around the hydrogens are very big. It's very shielded. There's a lot of electron density around those. And because there's so much electrons around those hydrogens, it tends to make the peak farther to the right or upfield from where most of my chemical will be. Most of my hydrogens will be downfield or to the left of the TMS peak. So with a lot of electrons around a hydrogen, that's called the shield. Those are called shielded. They're shielded with electrons. If a hydrogen atom has very little electron cloud, it's called a de-shielded hydrogen. So shielded and de-shielded. Shielded with a lot of electrons, de-shielded with very few electrons. The right side, or the upfield side of my NMR spectrum, is where the shielded hydrogens will be, ones with the electron density around them. And this side is where you have higher magnetic field. We have to increase the strength of our magnet. If we have a bunch of electron density, these negative electrons around our hydrogens, we need to increase the magnetic field in order to cause those to be in resonance or flip. Ones that are hydrogens that are de-shielded with few electrons around them, low electron density, they'll tend to be on the downfield side or lower magnetic field side. So this side are shielded with a lot of electrons, this side more de-shielded with fewer electrons. So let's take a look at one example. This is methanol. Methanol, if we look at our spectrum, TMS would show up right here at 0. It's not on this scale. So that's how we would know where 0 is. And we have one hydrogen, this blue one, on the alcohol hydrogen, where it's got low electron density because this electronegative element, this oxygen, has pulled some of the electrons away from the hydrogen. So it is de-shielded. We've pulled the electron density away. These three hydrogens, on the other hand, are not next to the oxygen, so they do not have electrons pulled away, and they are more shielded. So these red ones, being more shielded, show up right here. Looks like a little more than 3. And this blue one, this one right here, this hydrogen, shows up right here around 4. So we have 2 different peaks. One for the blue one, the hydrogen that's on the oxygen, it's by itself around 4. And the other 3, these 3 red ones, they all show up in the same place right here. So why do they show up in the same place? Let's see if we can clear it up so we can see it a little bit. Those 3 hydrogens are all equidistant from everything else inside of the spectrum. So this hydrogen, and this hydrogen. They're all the exact same distance away from the oxygen. They're all the exact same distance away from the carbon. So we say they are chemically equivalent. That means they all show up in the same place in the NMR spectrum. One more thing I want you to notice just briefly is this peak, this red peak, is bigger. It's quite a bit bigger than this blue peak. How much bigger is it? Well, you could guess it. It's 3 times bigger because there's 3 hydrogens for that one compared to 1 blue hydrogen, the alcohol hydrogen. So a couple things we're learning about our NMR spectrum. Different types of hydrogens show up in different places. The amount of hydrogens that are chemically equivalent and all show up in the same place, they add together and they make bigger peaks. And the relative size of those peaks depends on how many you have. If you have 3 compared to 1, you end up with 3 compared to 1 for the area underneath those peaks. Now that we have a brief overview of the hydrogen NMR, let's answer this problem. How many peaks would we expect to see in the hydrogen NMR spectrum for each of these following compounds? So let's take a look at the hydrogens only. We're just looking at the hydrogens. So on this one, we have an A, we have 1 hydrogen on an oxygen. These 2 hydrogens are on the same carbon, so they'll be the same ones. Let's use different colors here. These 2 hydrogens on the CH2 are 2 away from the oxygen, so they're different than the CH2 that's only 1 away from the oxygen. And these 3 are even farther away from the oxygen. So we have 4 types of hydrogens that would show up in the hydrogen NMR spectrum. So we would expect 4 different peaks. The smallest one would be this one with only 1 hydrogen. This would be too big. This would be too big. And this one would be the biggest peak with 3 hydrogens. But I'd expect 4 different peaks inside of the NMR spectrum. All right, this next one. The hydrogen on the oxygen is 1. This CH is 1. Now these 2 CH3s, this one and this one, are chemically equivalent. They're the same distance from everything else inside of the spectrum, or inside of this molecule. So these 3 would show up, these 6 hydrogens would show up in the same place. So we'd see 6 hydrogens for 1 peak, we'd see 1 hydrogen for this peak, and we'd see 1 hydrogen for that peak, but 3 different peaks. Let's skip C for now and go on to D. This one I have this hydrogen. This one's only 1 away. This CH3 is 2 away. Let's use a different color. Now this CH2 is different yet because this CH2 is closer to this CH3, and this one, the green one, is very far away from that CH3. So they're different. And this CH3 is a different one because it's a different chemical environment. So this one would be 1, 2, 3, 4, 5 different hydrogens that would integrate to 3, to 2, to 3, just 1 for that one, and just 1 for that one. That would be the size of the area underneath those peaks. But we would expect to see 5 different peaks for that one. right, I think we're getting better. Taking a look at this one, can you see how many? Count them first. Did you get 1, 2, 3, 4, 5? Those are all different hydrogens, different groups. These 3 would be in one peak. That would be one peak. This one would be one peak. This peak would be 2 high, an area of 2. And this would have an area of 3, but 5 different peaks. And then finally this one, we have 1. This one's 1 away from the OH, those 2 hydrogens. These 2 hydrogens are a couple away. These 2 are even farther away. And these 3 are even farther away. And they would integrate. So I'd have 5 different peaks. This one would be tiny with a 1 hydrogen area, a 2 hydrogen area, a 2 hydrogen area, 2 hydrogen area, and this would be the biggest one with 3 hydrogens in that peak. All right, let's come back to this one. You might think that these are equivalent and this one is, since these are 90 degrees and this one looks like it's 180 degrees, but of course that's not correct. That's drawn flat, but that's not really what this looks like, right? Let's draw this out. So we have the alcohol on a carbon, and we have a tetrahedral shape around that carbon. Whoops, CH3, CH3. So this one right here is 1, of course, that's different. It's on the oxygen. But these 3, and these 3 hydrogens are all chemically equivalent. So they'd be 9 hydrogen tall for one peak and 1 hydrogen tall for the other peak. So we'd have a really big peak for those 9. But we'd see 2 peaks overall for C. I hope that helps. You have a general idea. The peaks end up looking a little more complicated. They'll change different shapes. We'll get to that soon. Where they show up, called the chemical shift. We'll get to that soon in a different video. But if you can help me out, if this is helpful for you, please subscribe to this channel, like this video, maybe comment if this is helpful, and help others find my videos so we can help them also learn more about organic chemistry.